So, good afternoon, everyone, and welcome back to the Prisma seminar. Today, we have the pleasure to have Ilya Chevyrev from Sissa and Shen from Wisconsin University. And let me first briefly say a few words about the first speaker of today, who is Ilya Chevyrev. And so let me tell you that Ilya is, well, as I said, is working now at Sissa in Trieste since a few months, actually. And Ilya got his PhD from Oxford in 2016 under the supervision of Terry Lyons, and where he was working on rough paths, regularity structure, not really regularity structures, but signatures and these kind of things. He then moved on for a postdoc in Berlin under the mentor, with mentor Peter Fritz, still working on rough paths a bit. And I was at the same time, or basically the same time, also research fellow at Oxford, at the St. John's College. Then he moved on with a position in Edinburgh as a reader, and now he's back not back. Now he's in Italy, and we are very happy to have him here. So at Sissa. The interests of Ilya are various. He worked on SPDEs, regularity structures, rough paths, quantum field theory, as we will see today, but also homogenization. There are many distinctions that he got, and I just say a few. He recently got 2025 the Frontiers of Science Award, in 2024 the Rollo Davidson Prize, and he was awarded with an ERC starting grant in 2023. He's associate editor of Probability in Mathematical Physics and Stochastic Processes and Applications. And it's very much a pleasure to have you here to give this talk on stochastic quantization of gauge theories. Please, Ilya, go ahead.
Well, thank you very much for the kind introduction and for the invitation to speak here. It's a pleasure. So today, with my collaborator and friend Shen, we'll be speaking about stochastic quantization of gauge theories. So these are based on joint works from we'll mostly be describing joint works from a few years ago. One of them is already over 5 years old, which the first two are based on jointly also with AJ Chandra and Martin Heirer, and the last one was co-authored by myself and Shen. Okay, so just to set the scene. Let's see. Most of the talk will be focusing on certain types of Euclidean quantum field theories. So as Alberto mentioned, this is one of my mathematical interests. So I'll try to describe it from a probabilistic perspective. So for the purpose of this talk, we can think of a Euclidean QFT as essentially a probability measure on functions. So these are functions which are from the domain is Rd, and they take values in potentially some vector space like Rn. And they're given by a Gibbs type weighting like this. So here dA is supposed to be some sort of a formal Lebesgue measure on the space of all functions. And the S of A appearing inside the exponential is some sort of an action. So here we'll take actions to be the integral over the space Rd of some sort of a Lagrangian density. So this could be some sort of a function involving the field and its derivatives. So these kinds of Euclidean QFTs appear in several different areas. So I just want to motivate why they're interesting to study. So they appear in at least 3 areas. One of them is the first one is constructive quantum field theory. So this is supposed to be somehow a model for these Euclidean QFTs naturally arise as in the description of elementary particles. So we know we can smash particles together in accelerators and get pictures that look like this, but actually at present we still lack a rigorous mathematical foundation for these for describing these collisions and scatterings. So to a large extent, we still don't really understand on a rigorous mathematical level. So this is these Euclidean QFTs arose in the desire to create a mathematical model for these for elementary particles. Another field is in statistical mechanics. So this is often these probability measures arise as scaling limits for certain statistical mechanics models, like Ising models, or most recently this was shown for Bose gases. And in other areas also they arise in analysis of PDEs. So these Euclidean QFTs can be seen as invariant measures for certain evolution equations, like the nonlinear wave equation or the nonlinear Schrödinger equation, and these equations keep these probability measures invariant. And then one can actually build good solution theories for these PDEs, like global solution theories, in situations where classical kind of deterministic analysis might break down. So they can help in analysis of PDEs as well. Okay, so this is just to hopefully motivate you, that provide some motivation for why these are interesting to study. And so what are the difficulties in studying them? So there's kind of, I like to think of it as there's two types of problems that arise when looking at Euclidean QFTs. So there's the ultraviolet problem, which is the fact that we're dealing with RD as opposed to a lattice, ZD. So the points can be arbitrarily close to each other. And the second one is an infrared problem, which is that we're working over RD instead of a box. So somehow fields are defined over the whole space instead of some sort of a compact domain. And both of these things in different ways make the definition of this action kind of non-trivial. So somehow maybe the field A is supposed to be stationary, but then if it's defined over the whole space, then the action or Lagrangian density is just infinity when you integrate it over RD. And so that's kind of an infrared, and in the ultraviolet, maybe you realize that A should be supported in a space of distributions as opposed to functions. I'll speak about this a little bit later as well. And then when you look at the products inside of the Lagrangian, it's not really clear how to make sense of them. Okay. So these are the difficulties that arise when studying Euclidean QFTs. So I'm going to be now, so that was a very generic setup. Now I'll be speaking about a specific model that Hao and I will be speaking about today. So I'm going to introduce this model essentially through an example. So the model is called Yang-Mills theory, or the Yang-Mills model. And the simplest version of Yang-Mills model actually was already around much before Yang and Mills introduced them in the 50s. So the simplest Yang-Mills model is actually Maxwell's equations for electromagnetism. Or Maxwell's theory for electromagnetism. So I'll introduce this first, and I'll kind of, just to motivate where the various constructions that appear in gauge theory arise already at the level of Maxwell's theory. So we're going to consider fields E and B. So these are fields on R4. So R4 here is space and time, so 4-dimensional, and they take values in R3. So these are the usual kind of vectors that point somehow in 3-dimensional space that we think about, giving the electric and magnetic forces. So if we write down Maxwell's equations in a vacuum, they look like this. So don't think so much at the moment about these equations. If you're not familiar with them, it doesn't really matter. But they actually have well-known solutions. So they're kind of these traveling waves. So they have many solutions. Any traveling wave like this is a solution to these equations. But the thing that I want to point out about them is that this is a system of 6 real variables. So because there's 6 of them, because there's 3 for the electric and 3 for the magnetic. But there's 8 scalar equations in total, because this first equation is really an equation for these 2 equations in the first column are really an equation for scalars, because the objects inside of them is a scalar. But the second 2 equations are vectors. So B is a three-dimensional vector, so its derivative is a 3-dimensional vector, and so both of these together add 3 more equations each. So there's 2 plus 6, so that's 8 equations. And so at first it might seem a little bit strange. Where do these numbers come from? So you have 6 real variables and you have 8 scalar equations. So it's not a priori clear that there are solutions to this equation, because it might be overdetermined. It's somehow kind of overspecified in some sense. Yeah, we'll try to find now a different way of looking at these equations, where these numbers might become a little bit more which will explain where these numbers come from. Okay, so instead of considering directly the electric and magnetic fields, we're going to consider a one form. So a one form is a function from R4 into R4. This is in physics called the gauge field. And we're going to define its curvature 2 form, which is just the usual exterior derivative of A, if in the language of differential geometry. So the exterior derivative is given in this form. So this is an antisymmetric, think of it as an antisymmetric matrix F. So if you swap the entries I and j, you swap the sign. Okay, and then we've taken this arbitrary one form A, we've defined its curvature 2 form, and now we're going to define fields E and B according to this big matrix. So here I said you should think of F as a big antisymmetric matrix. So this is the big matrix. We're going to set E and B to be according to these kind of values so that they match what's on the right hand side. Okay, so we define E and B using A through this curvature 2 form. Then an important remark here is that because we've defined F this way, as the exterior derivative of A, essentially a special case of the Bianchi identity tells us that the square of the square of this exterior derivative is 0. So the exterior derivative of F is actually 0. So if you take the exterior derivative of this 2 form, then it becomes 0. Because F is not a generic 2 form. It comes from the exterior derivative of a 1 form. And so when you go back to what that means for these equations E and B, that essentially means that the first 2 of the Maxwell's equations from the previous slide automatically hold for these fields E and B with this definition. Okay, so we've kind of recovered half of Maxwell's equations just from this special choice of E and B using this one form A. Okay, so what about the other 2 Maxwell's equations? So the other 2 Maxwell's equations are equivalent to a very similar looking equation, but this time it's not automatically satisfied for any A. So the other 2 Maxwell's equations are equivalent to D star of F equaling to A, where D star is the adjoint of D. So this is the exterior derivative maps 2 forms to 3 forms, and its adjoint maps 2 forms to 1 forms. So this should be thought of as an equality between 1 forms. Okay, so this ensures that the other 2 Maxwell's equations are satisfied. So this is something one can check somehow by hand. It's not maybe just take my word for it for now. Okay, and then this equality holds if and only if A is a stationary point of the so-called Yang-Mills action. So if we introduce this action, which is the L2 norm of the curvature, and you look at its variations, then the critical points of this action are precisely the 1 forms A for which D star of F is equal to 0. So what we've managed to do is rewrite Maxwell's equations in terms of a 1 form, and the first 2 Maxwell's equations automatically hold because it's essentially equivalent to D squared is equal to 0, and the second 2 Maxwell's equations are equivalent to A being a critical point of this action. So the point here is that we're kind of in a more familiar setting of maybe like this Lagrange principle of minimizing actions. So the classical equations of motions are given by minimizing an action. So this is the action that we want to minimize to get the classical equations of motion. Okay. And so, but this kind of rewriting, it came with a bit of a price. So what's this price? The price is that this curvature F, it doesn't actually determine A uniquely. So the physical quantities are always the electric and magnetic fields, and A was somehow just a mathematical construct in order for us to be able to write down Maxwell's equations in this very convenient form. So the way that F of A doesn't determine A uniquely is given by the fact that if you take A and you add to it the derivative of any function, so take any function from R4 to R, then the curvature does not change. And this is again a special case of the fact that the exterior derivative squared is equal to 0. So starting off with any A plus D of F always gives rise to the same electric and magnetic fields E and B. Okay, and this map from A to A plus DF, this is called the gauge transformation of The kind of the important fact is that we're not really interested in the one form A, but we're really interested in A plus any gradient, the gradient of any function. And this kind of equivalence class of one forms or gauge fields, A, so A plus the derivative of any function. This is called the gauge orbit of this one form, and this is the object that's physically important. So somehow A is just the mathematical construct or representation, but it's not unique, and it's really this equivalence class of A's when you shift it by any gradient. That's physically important. So by the way, if there's any questions during the talk, just feel free to write and or ask. So. Okay, so this was just an introduction to a very simple case of Yang-Mills theory, so Maxwell's equations. So now I'll introduce the actual model that we're interested in, and and I'll explain how it's related to this the construction I just gave. So we're going to fix so general Yang-Mills theory is given by the following two ingredients. We're going to fix any compact connected Lie group G, which we think of as a subset of the unitary n by n unitary matrices. So these are unitary matrices with complex entries. And we're going to call by little g its Lie algebra. So this is a Lie algebra of skew Hermitian matrices, n by n complex skew Hermitian matrices. And you will actually essentially lose nothing in the talk if you think of G as being equal to UN. So if you want a concrete example, just take G is equal to UN. So maybe U2 or U3. These are already non-trivial examples. And then the dynamical variables. So these are going to be the A that was the kind of the dynamical variable from my Euclidean QFT perspective are going to be one forms from RD into GD. So these are going to be so in the case of Maxwell's equations, we had gauge forms that had 4 components. So here we're going to have D components in general dimension D, but each component is a G valued, so it takes values in the Lie algebra. Okay, and then the underlying action is going to be very similar to what we saw before. It's the L2 norm of the curvature. So here I write it explicitly in terms of matrices. So this is where I pick the Hilbert-Schmidt inner product on matrices. So this f of A is the curvature. So and this curvature now looks similar to before, but instead of just having these partial derivatives of A, it also picks up a Lie bracket. So this is this bracket is the Lie bracket that's in the Lie algebra. So for matrices, this is just so the Lie bracket of x and y is just x times y minus y times x. So the usual Lie bracket. So examples of this, well, we've already seen actually one example. So this is when we take G to be U1 and the Lie algebra to be the imaginary line. So if one works this out, then one actually really recovers exactly the construction that we had before with Maxwell's theory, and of particular relevance to theories like the standard model. To recover quantum chromodynamics, conjecturally, one should take the group G to be SU3. So this is another interesting example. So this is so it's kind of somehow a non-abelian Maxwell's equation. And then to remind you, what we want to do is to define and study the following probability measure. So this is the Euclidean QFT that we're interested in. So now I think I finally kind of motivated and came to the point of where so this is the concrete Euclidean QFT that we're going to be interested in studying. Okay. So then, just to remind you, what kind of the difficulties with this construction. So there's a couple of generic difficulties. So first of all, there's no Lebesgue mesh on the space of one forms. So this D of A doesn't exist. So this is something that's common for all Euclidean QFTs. And moreover, this kind of an argument based on essentially perturbation theory. So if you think that this field theory should be at least as good as the Gaussian free field or something, then should have similar regularity as Gaussian free field, which is kind of a nice Euclidean QFT in D dimensions. Then this probability measure should actually be supported on distributions and not functions. And so these cubic and quartic terms that appear in the Yang-Mills energy, so the Yang-Mills energy has this quadratic term in A that comes from the non-abelian nature of the group. And when you square the f, this will produce terms that are cubic and quadratic, and quartic, cubic and quartic. So these are problematic terms inside the action. So there will also be quadratic terms, but your quadratic terms are kind of nice because you usually absorb them into some sort of a Gaussian measure. So these cubic and quartic terms suggest that the measure should actually be non-Gaussian. Okay, and so these are generic difficulties for all QFTs. But then for all interacting QFTs essentially, but gauge theories have this extra complication, which was what we saw from Maxwell's equations, that the one form A was not the physical object; it was the one form A plus the gradient of any function. This kind of this equivalence relation that was important. And so so here in the general setting, there's an analog of that. This analog is given by essentially an infinite dimensional symmetry group called the gauge group. So we're going to say that two one forms A and B are gauge equivalent if B and A are related by this relation for some sort of a function g that goes from Rd into the group G. So this is a generalization of the so for example, if the group is abelian, then this G and this G inverse would just cancel. So, but these are all just matrix products. So there's somehow these are all just products taking values in matrices. So if G and A commute, then this will just be A as well, and this will be just the derivative. Essentially, this will be the derivative of some sort of a function. So this is it boils down exactly to what we saw in Maxwell's equations. But in general, in the non-abelian setting, you get this kind of you get this form. Turns out that this is the correct notion of gauge equivalence. And so there's a postulate essentially in the physical models that are arising from gauge theories, which is that only the equivalence class of A and B should be, so only the equivalence class of A should be physically relevant. And so if A and B are gauge equivalent, then they're physically identical. And also in particular, their Yang-Mills actions agree. So what we really want is a measure not on the space of one forms, which here I denote by omega, but we really want it on the space of one forms quotiented by this gauge equivalence relation. And the space is somehow a bit complicated. It's a nonlinear space, for example, whenever G is non-abelian. So we're kind of outside the distribution theory, the kind of usual distribution theory for scalar bosonic theories that like the 5-4 theory. So this is somehow a feature distinct to gauge theories. Okay, so just to say a few words about the history of people looking at this problem. So in 2 dimensions, it turns out this model is exactly solvable or integrable, and you can write down its essentially its endpoint correlation functions for nice observables, which are called loop observables or Wilson loop observables, and you can write down precisely what the correlation functions for these observables should be. So this was already noted in the 70s in physics literature by Migdal, and then was developed by mathematicians to a rigorous level in kind of the decades since. And actually, this is still quite let's say, a rich area of research, especially when one kind of tries to vary the group and try to understand what happens. So the 2 dimensions is sort of I think unequivocally the best understood case that we have. In 3 and 4 dimensions, the situation is much more dire somehow. So there's only partial. So we only have results when essentially the group is abelian. So like U1, there you can construct both ultraviolet and infrared limits, and you get a Gaussian measure as you expect. And for general groups, there was work in the 80s and 90s, but this so by Balaban, Federbush, Manen, Rivasson, and Senor, which were basically based on renormalization group techniques. But by and large, it's the construction. So the kind of the rigorously establishing that you can define the Yang-Mills measure in dimension 3, even in on a compact domain, is essentially open. So these works were made very important progress, but they didn't quite achieve this constructing an actual measure and understanding its observables. And there's been a bit of a revival in the probability theory community over the past decade. So there's been a lot of interest coming from different communities in probability theory. So here I just list some names. It's a non-exhaustive list, and the purpose of this is just to give some examples of the people that have worked on questions related to Yang-Mills either in the lattice formulations or in the continuum. And as I mentioned, in 3 dimensions, the construction is essentially open. Okay, so let me give some the remaining time that I have. Let me now kind of set up or try to describe the setting of the actual papers that I mentioned at the beginning of the talk, and some of the results that we have in this direction. So and I'll make specific precisely our setting now. So we're going to be interested in studying this Euclidean QFT, so this Yang-Mills quantum Yang-Mills theory through its Langemann dynamic. So the Langemann dynamic associated to any Gibbs type probability measure like this is essentially a stochastic evolution like this, which comes in 2 parts. The first part is a gradient descent term, which essentially, so if you think of this as a ball rolling in some sort of an energy landscape, this term always pushes the ball down the energy landscape, so it wants to go down. And the second part is a stochastic forcing term, which essentially creates random perturbations as the ball rolls down. So maybe the ball in general wants to kind of roll down the energy landscape, but this noise will push in lots of different directions. So it'll create maybe a trajectory that looks like this. Okay, and this idea of using this, so Langemann dynamic is very classical for probability measures, but it was introduced in the context of Euclidean QFTs by Parisi and Wu in the early 80s. Who were actually motivated by gauge theory. So they kind of saw the use of this Langemann dynamic as a way to overcome this problem with the gauge equivalence classes that I mentioned. So they kind of saw this as potentially a different way than classical path integral formalism to quantize gauge theories. And so this method of using the Langemann dynamic has been so if you write this equation down for a generic Euclidean QFT, you realize that this is essentially a stochastic partial differential equation. So this the term on the right hand side, for example, will have a Laplacian term if your action contains maybe a gradient, like the usual kinetic term, which is the gradient squared. Gradient squared term, plus certain nonlinearities that depend on your action. So this is some sort of a stochastic PDE. And there's been a lot of progress recently made over the last decade. So with, in particular by introduction of the theory of regularity structures and power control distributions and renormalization group methods, which now make rigorous sense of these solution theories. So this method of using the Langemann dynamic to study the measure. So we know that this sort of the motivation for this Langemann dynamic is that it keeps this measure invariant. So if you understand the behavior of the Langemann dynamic, you can learn properties about the measure. You can give its constructions, maybe give tail estimates, and verify certain properties of them. So this idea has been very successful for certain scalar bosonic theories. So I mentioned here some contributions to this. Especially successful for 5-4 theories. So our motivation in these works was to kind of try to extend this to non-scalar theories like a gauge theory. Okay, so here's the kind of the picture that I want to draw of what one expects from the stochastic quantization procedure for gauge theories. So this is here I write down this Langemann dynamic. Specifically for the Yang-Mills action. I write essentially in this generic term, but I just take the Yang-Mills action now. And I'm going to write in the superscript this little a, meaning for the initial condition of A. So I think of this somehow as a diffusion on the space of fields. So I want to be able to solve this stochastic PDE, and I think of this as a diffusion in the space of 1 forms. So omega here is the space of 1 forms. And so you should think of this maybe as the picture is somehow 3-dimensional. So the space of 1 forms is 3-dimensional space, but then the space of equivalence classes is this maybe this disk here, which is like a 2-dimensional object. And so for every point on this disk, there's a black line, which is the space of equivalence classes. Maybe this picture is also deceptively simple because these gauge equivalence classes are not really straight lines in any sense, but just for illustration purposes, think of it like this. And so what one expects after analyzing this equation is the following. So if we start the dynamic from a one form A, and we let it run for time t, then we arrive at some sort of a point here. And if we start the same dynamic but from a different point B, and we let it run for time t, then we end up at a different point. Then there's no reason that these two trajectories, the magenta one and the green one, should be equal to each other or close to each other in any sense, because after all their initial points were different. But what turns out to be, there's a formal heuristic argument that you can write down, which essentially uses E2 isometry, which is that if you project down these two solutions to the space of gauge orbits, then this final point of A started from little a and A started from little b, so their final points should be equal to each other when you project them down to the space of gauge orbits in law. So there's somehow an equality in law when you project down for any time these solutions. So somehow I mean, here I kind of draw it as a almost sure, like somehow it looks like an almost sure quality because they project down to the same kind of trajectory here, but this is really an equality in law. I don't really know how to draw equality in law, so I draw it like normal equality. So somehow this Langevin dynamic should project down to a probability. So somehow it should project down to a diffusion at the level of gauge orbits. So it should give rise to a Markov process on the level of gauge orbits. Okay, and actually at the level of this equation, before we change anything to do with it, which I will do on the next slide, the equality between this distribution and so there's a precise kind of relationship that you expect from these two, which is that B will solve the same equation driven by so if there's a gauge transformation that sends A to B, then the B will solve the same equation as driven by A. So the gauge transformation sending A to B will essentially be the same one that sends little a to little b, but the noise gets conjugated by this gauge transformation G. And so that conjugation keeps the noise the same in law, and that's why you get somehow equality in law between the two diffusions. So this is like, as I mentioned, this is a form of E2 isometry. Okay, so this is the heuristic that one expects from a formal calculation to do with this Langevin dynamic that one can do. Okay, and so now let me now present kind of this and the next result that I present is essentially the only results that I will state. So this theorem is a bit heavy when you see it, but essentially, if you were to take anything away from it, it's the fact that this heuristic that I just presented on the previous slide can be made rigorous. So, and the precise way that it can be made rigorous in dimensions 2 and 3, and on finite volume. So I should state right away that I work on the torus, so I don't work on the whole space. I compactify the space because this avoids a lot of complications. And then the idea is that if I take G to be Xi to be a white noise so time times the torus, and I take a mollifier, then if I look at this mollified equation, so I look at the equation solved with a mollified noise, then and I insert two terms into it. I insert this blue term. This blue term is called a de Turk term, and it basically makes the equation parabolic. But so without this term, the equation would not be parabolic. And it's constructed in such a way that it acts tangentially to gauge orbits. So this kind of adds a drift to the equation that when you project down to space of gauge orbits, it doesn't change the dynamics. So this is kind of a valid term to add if we're only interested in the evolution at the level of the gauge orbits. And then we also insert this extra red term, C epsilon of A epsilon. So these are linear operators from the Lie algebra 2 itself, which are renormalization terms. And the purpose of them is that they help the equation converge. So especially in dimension 3, without this term, the equation would not converge. And moreover, they have to be chosen in a very precise way in order so that when you project the limiting process as epsilon goes to 0 to the space of gauge orbits, you pick up you get a Markov process. So it makes this this picture that the magenta and the green guy project down to the same process downstairs correct. So that's essentially the statement of these two. So the main point of the theorem is this second point, that if you choose C epsilon correctly, then the limit of these solutions as epsilon goes to 0, so as you remove the modification. When you can project it down to a space of gauge orbits, and this process will now be Markovian on this quotiented space. And an important caveat here is that both A and the projected process are possibly have finite time blow up. So at this point we didn't know that they have global and time solutions. And also just on the second line, I write down the heuristic form of this equation. So here I write everything symbolically, but here now, so this is when you combine all the terms together, you get it. So essentially, the solution for this this SPD looks like a nonlinear heat equation with a cubic term and a quadratic term with A in its derivative. Okay, so this is the first two results that so the first paper is we handled dimension 2, and the second paper we handled dimension 3, and then in another paper that we put on the archive a year after this 3-dimensional paper, we looked at the global solution theory for dimension 2. So this is the kind of the second result. So the previous result was essentially completely local in time. And we were interested in understanding whether, at least for dimension 2, I mentioned before that this Yang-Mills probability measure was integrable. So somehow, so we know what its correlation functions should be, and we know how to make sense of it in some way. Then can it be? Is this Yang-Mills measure in some sense actually the invariant measure of this Markov process on the space of gauge orbits? And the answer is yes. So this was the second result that I wanted to mention. So there's this probability measure in dimension 2, and so the Yang-Mills probability measure, and in a way that you can make precise, it's the unique invariant measure for this Markov process. So this kind of answers the first positive answer. So in some sense, this creates a connection between the Yang-Mills quantum field theory and the actual stochastic PDE. So before, like in the previous kind of slide, these two things are unconnected. This was just an analysis of the SPDE, and this result kind of connects the two together. And this has several, and so there were several results that actually appeared in this paper. This is perhaps the most important one. But as a corollary, we also established that this dynamic on the level of gauge orbits is global, so it doesn't actually blow up. And this we only know in dimension 2 because of this invariant measure argument. It's also as a kind of the method that we proved this result also actually proved a universality statement for this dynamic. So it's this dynamic on the level of gauge orbits is actually universal for many lattice models. So you can discretize the Yang-Mills action in various different ways with lots of different local interactions. But as long as the local interactions are somehow natural, then they all give rise to the same limiting dynamic when the lattice spacing goes to 0. This was one of the results in the paper. And also for kind of independent interest, we actually showed that this renormalization operator, C epsilon, so first of all, it's a constant. It actually, because of some sort of cancellation, it doesn't diverge as epsilon goes to 0. So kind of there's diverging constants that cancel each other. So it's actually, you can take it as a constant. And this is specific to dimension 2, and more importantly, this we already actually knew from previous works, but the important thing here is that it's actually also unique. So there's really only one constant you can put into the equation to give this gauge covariance property. Yeah, so this is so these were essentially all the kind of I wanted to so I've already gone over time, so I wanted to just state these results. Maybe a final comment is that it's curious that inside of this dynamic, this modification of the noise that actually breaks gauge covariance, but also the insertion of this term also breaks gauge covariance. So this formal argument with E2 isometry that I mentioned, that things project down and should give rise to the same law, it fails at the positive epsilon level. So somehow, but it fails in such a way that this failure cancels. So this renormalization constant and this modification, they both break gauge covariance, but then this breaking of gauge covariance is cancelled in the limit. So it's somehow interesting that you only have this Markov property at the in the limit, not at positive epsilon. So this is maybe just an interesting remark. And so I think in the second talk, How will kind of maybe present elements of this result a little bit more, maybe present some corollaries of this result. So stick around to see to see more on this. So, and I will thank you for your attention.
Thank you, Ilya, for the very nice talk. And other questions? I have one question. So in this theorem in dimension 2, you prove that the Yang-Mills law is the unique invariant distribution for your limiting process, right?
That's right. Yes. Yes.
What is known in higher dimensions about this process? Because in the previous theorem it was also for higher dimensions, right?
Yeah.
Also, for dimension 3, do you know that this limiting process has a unique invariant distribution or something like that?
No. This this is not known at the moment. So this would be, in some sense, this would actually solve this problem about the construction also of the three-dimensional Yang-Mills. So this will be very interesting to establish.
Yeah.
This would be very, very nice. But no, at the moment it's not known. No.
So I think since it's already 4:45, we thank Ilya Chevyrev, Ilya again for the very nice talk.
Thanks a lot.
And I suggest we move on to how. So maybe you can try first to share the screen.
Yeah.
Okay, it works. Maybe you go full screen.
Yeah, full screen. Yeah, I can do full screen.
Okay, perfect. Try to go one slide forward and back just to see. Okay, perfect.
Okay.
Maybe Sonia, and then you present.
Okay, we can start. So the second speaker of today is Professor Shen from the University of Wisconsin-Madison. He got both his bachelor and his master at the University of Pekin and his PhD at Princeton. After that, he held several research positions in the US and in the UK. And since 2018, he has been at the University of Wisconsin-Madison, where he has been full professor since May 2025. Well, his research interests focus on stochastic partial differential equations and application to mathematical physics, especially to quantum field theory. He received several grants and prizes, and he is associate editor of Annals of Probability, Analysis and Poincaré, and also Stochastic and Partial Differential Equation Analysis and Computation. Today, we are very glad to have him here to present the second part of his talk, his results about the stochastic quantization of gauge theories. So please, Al.
Thank you very much for the invitation and the introduction. So this is part 2 of the talk. In the first talk, Ilya explained that for the quantum Yang-Mills theory, we want to make sense of the formal measure, which look like exponential of this Yang-Mills action. So so actually so Ilya also mentioned in 2D the model has integrability. So let me explain in a more detail why is this case. So in 2D there's actually a nice gauge transformation which is called axial gauge. So what's special here is in 2D the field A has only two components. Now uh, the axial gauge says that there is actually a gauge transformation which makes one of the two components zero. Uh, I can show you an example of this calculation. For example, in the abelian case, if the group is U1, then in that case, the A1, A2, this is just the regular, the usual vector field. So each of A1 and A2 are just a scalar. In this case, in abelian case, the gauge transformation is just shifting the vector field by a gradient. Um, so now we can see that we can choose the f, for example, to completely kill the second component because, for example, we can just choose the f to be the antiderivative of A2. So this whole thing is zero. Of course, with this choice of f, this is still non-zero. Okay, so we can only kill one of the components, but not all the components. But in this case, what's nice is that okay, this also happen in non-abelian case, in general case, and then the so-called curvature, which is defined to be this, so it's a linear part plus Lie bracket of A1, A2, which is nonlinear. If we can make A2 zero, then this nonlinear term vanishes. So we're left with only D2A1. In other words, the curvature becomes linear and this whole action becomes quadratic. And if the action is quadratic, then essentially the measure becomes Gaussian measure. And this was special in 2D. So in higher dimension, even if we kill one of the components, the curvature is still nonlinear, so it's still non-Gaussian. And this is why in 2D, there are actually a lot of large literature starting from maybe Bruce Driver and Langross and so on. They can use this sort of Gaussian structure to exactly compute many correlations. Okay. Now, in the first talk, we see this our result with Chandra, Chevyrev, and higher. We show that in 2D and 3D on a torus, we have a local well-postedness. And just remark that actually we prove a stronger result, which says that it's not only that our solution live in the so-called best of space, but actually we construct a new space, which is a subspace of this space of distributions or best of space. And our solution lives in this new space. And why do we construct a new space? Because later we want to define something called observable or Wilson loop, also called holonomy. And the difficulty to make sense of such so-called holonomies is that essentially they are sort of non-abelian version of line integrals of vector field. So in general, for distributional vector fields, we don't have a notion of line integral because they don't have a notion of pointwise value. So that's why we actually, in this paper, we construct a new space called omega. And in this new space, every element has a notion of line integral and holonomy. Okay, so but this is about the local well-postedness. We need to do renormalization, and with the right normalization, it converges as epsilon go to zero. Also, another remark in 2D, actually, this renormalization term is order 1. If you know some singular SPD, usually the renormalization blows up. So usually, for example, in 3D, this C epsilon actually blows up like 1 over epsilon. But in 2D, actually, this is order 1. Actually, in 2D, there are like 3 divergent constants, but they cancel out. So their sum is actually order 1. You might wonder why we put this order 1, this finite renormalization, right? We can also choose that to be 0. If we choose that to be 0, we also have a limit. But this limit actually depends on this parameter C, this renormalization C. In other words, we have a family of solutions depending on the choice of this renormalization. And this is actually related with the second part. There's a right choice of this C. Right? Although C is finite, we don't want to choose that to be zero. There's a special value, a special choice of this C, so that the solution has the following gauge covariant property, as Ilya already mentioned. It says that if we start with two initial conditions which are gauge equivalent, then after time t, they're still gauge equivalent. In other words, this is really a dynamic living on the quotient space. So the dynamic doesn't care which sort of representative element we choose from this gauge equivalent class, right? So we choose any, we start from anywhere from this gauge equivalent class, then we at time t we just have a solution in the same gauge equivalent class. So in other words, with this nice property, we can project the solution to the quotient space, and that gives us a so-called Yang-Mills process X, which is a Markov process on the quotient space. And this is our main result in the so-called CCHS paper. So in this paper, this projected process, Yang-Mills process on the quotient space, only exists. We only know the existence for short time. In the end of Ilya's talk, we mentioned our newer result, which says that on 2D torus, actually, we can extend this Yang-Mills process for all time. Okay, so in this paper, we proved the following four results, but the main result is that this process exists for all time, and also, indeed, we have a unique invariant measure um, uh, called mu ym that lives on the quotient space. So this is only in 2D. As Alberto asked, we so far we don't have this result in higher dimension. So actually, in order to prove this result about a unique invariant measure and existence for a long time, we use the general philosophy of Jean Bourgain called the Bourgain's argument. In this argument, we need to go through a finite dimensional approximation. And this is why we actually look at a lattice Yang-Mills model. And this is a class of lattice models which have a huge independent interest studied by a lot of other people. We show that on the lattice, we can explicitly check the discrete measure is invariant measure. Okay, that's why we like to start with a finite dimensional lattice, because on lattice we know well-posedness, we know invariant measure, and so on. And then we pass the limit. And this is our general philosophy. Okay, so and also there's part one, which says that actually not only that we know there's a special choice of C such that the solution is gauge covariant, also we know such a choice is unique. This is very important for us to identify the scaling limit of such lattice models. So far we stated all the results. Let me maybe summarize again all the results with the following picture. So we studied the SPD, which is this evolution equation, stochastic SPD. Using regular structures, we can show that in the model in the space of distributions, basically some sort of C alpha space with negative alpha, we do have a solution for such SPD. I also mentioned that in the CCHS paper, we construct new space. Actually, we prove a stronger result that our solution lives in this new space, not one of those classical distribution space, but as actually this space called omega. And what's special in this omega is that every element in this omega, we have a good notion of line integral, so-called Wilson loop observable. And then we show that there's a unique choice of the renormalization such that the solution is gauge covariant. And the gauge covariance property allow us to project the solution to the quotient space, right? So this is the space of one forms quotient out the gauge equivalence relation. So the projected Markov process is called X. Right? So X doesn't satisfy any equation or something. X is really the projection of the equation to the quotient space. So in some sense, X is sort of implicit, not as explicit as SPD. But it is this projected process X which has a unique invariant measure. And also this, so I mentioned that because of the special axial gauge in 2D, there was a lot of study by Driver, Levy, and Langros, and many Sengupta, many people. They can exactly compute correlations of Wilson loop observables. Um, we show that this invariant measure for our Markov process, indeed, if you look at the Wilson loop observables for this measure, you view those Wilson loop as a marginal law of this measure, then the marginal law indeed coincide with earlier work. So, by the way, I should mention that Ilya, before all these papers, Ilya also has a single other paper around 2019. He also showed that indeed there is a distributional random field A whose holonomy also coincide with those early works. But with our dynamical approach, so that early paper by Ilya didn't use any dynamic, didn't use any PD, SPD. But our dynamic approach has some advantages. For example, we can prove some very interesting corollaries. So in this corollary, we prove that you can think of the Yang-Mills measure as two parts in some sense. It has a decomposition into a Gaussian free field, so a Gaussian part, plus a more regular part. Right? So this part is almost C1, so it's like almost a differential function. So there's some when we project to the quotient space, and that gave us the Yang-Mills measure. So this is a nice decomposition of the Yang-Mills measure. And also, since we go through this in the Bourgain's argument, as I already mentioned, we go through this lattice approximation, right? So we show that dynamic of lattice models as lattice spacing go to 0, they convert to our SPD. And because of this approximation, all those lattice models will prove the universality result that as the lattice spacing go to 0, the invariant measures or the lattice models actually converge to this so-called mu ym. So mu ym is the universal limit of all those lattice models. Okay. I think we want to learn something from this talk, so I'm not going to give any long proof, but I just mentioned the key ideas in our. So I mentioned 4 key ideas, and then for each of them I spend 1 or 2 pages to illustrate the idea. So I'll first explain what is the general idea of Bourgain's so-called globalization argument. It's about how to prove an invariant measure in infinite dimension and how to use the invariant measure to globalize a local solution. And then I'll mention some lattice model. Here we use some geometry, and then maybe I mention the uniqueness of gauge covariant. And here the key idea is to use observables to study some property, such as gauge covariant property of solution. So all this actually also, and then the moments. So this relies on some gauge fixing idea. So actually, all these ideas are in some sense very general, and I'll also mention how they show up in some other results. So Bourgain's argument is basically the following, right? So suppose we have some PD or some SPD or even ODE, it doesn't matter. Suppose we have some local solution. So local solution usually the theory is based on a contractive map, right? So some sort of fixed point map, some Picard iteration. And usually in local theory, we know that suppose the initial condition, right, x0 is the initial condition for some equation. Suppose we know it's smaller than some constant L, then the local theory tells us that on a short interval, we know the solution is bounded by say 2L. And we can make the depending on the structure of the equation, we know how small this interval should be. For example, we can choose this k to be L to the 100, right? The smallness actually depends on the size of initial condition. So uh, so now Bourgain has a very nice argument to extend this short time solution to long time to arbitrary interval from 0 to t. The idea is based on the following two observations. First, suppose the x has an invariant measure called mu. Okay, so actually in Bourgain, he was studying deterministic PDE, like Schrodinger equation. And Schrodinger equation also has invariant measure. So suppose we have some invariant measure, then basically in order to prove their solution over long interval, we need to argue that the probability that over long interval the solution is larger than this constant. This probability is very small as we wish. Right? They basically want to argue for this, and the idea is we can chop the long interval into subintervals of length 1 over k. Then, since we know x is stationary, the law of x over each of the subinterval is the same. So for x to be larger than L over this long interval, well, x has to be larger than L over one of the subintervals. So we can bound this probability by k, right? K is a number of subintervals times the probability that x is larger than L over one such subinterval. But we only need to look at the first subinterval because, as I said, the law of x over each subinterval is the same. Right? So this actually now boiled down to, in some sense, boiled down to local theory, right? So now this just the size of the solution over the first interval. The second observation is that is actually Markov inequality, right? Markov inequality says if we know the invariant measure has good moments, then the probability that the random variable is larger than L is bounded by L to the minus 10,000. Say, suppose we have moments of 10,000 order, right? So now if initial condition obeys this law, then we know the probability that this initial condition larger than L is super small. And from local theory, then we also know that over this small subinterval is also very small. Right? So basically the probability, this probability is bounded by something like L to the minus 10,000, which is much smaller than k, right? K is like L to the 100. So this is why we can make this probability as small as we wish. Right? So this idea by Bourgain was actually very influential to the study of Schrodinger equation and many other PDE, and also later applied to singular SPD. For example, in this paper, they use this idea for 543 equation. And for stochastic PDE, there's something more special than deterministic PDE, because so for a stochastic PDE, maybe we can prove strong Feller property, and with this property, we can show that actually we have global solution for every initial condition, not just initial condition which follow this invariant measure. Okay. So this is a general idea of Bourgain's global argument. In order to apply this to our problem, it's still very non-trivial. It's non-trivial because the two red assumptions here. The first assumption is assuming that we already know there's an invariant measure, but for us, we don't know, right? So we don't know yet in our infinite dimensional setting, we don't know yet if it is an invariant measure. So for our Yang-Mills program, we want to go through a finite dimensional approximation. In finite dimension, we already know there's a finite dimensional stationary solution and also a finite. So that's why we need to go through a so-called lattice Yang-Mills model. Right? There are of course other ways to do finite dimensional truncation, like Fourier truncation, but those would break the gauge symmetry. Okay, so also we need a good moment bound for the invariant measure. That's the second challenge. Okay, so let me just quickly introduce you the lattice Yang-Mills model. These are also of independent interest, and recently many people such as Saurav Chatterjee and so on, they just look at a lattice Yang-Mills model and derive many correlation decay and many other properties. So, in this model, it's like a statistical physical model, right? So every edge there's a spin, and the spin now take value in the Lie group actually. So usually the spins are defined on the vertices, but here is actually on the edges because they want to discretize the one form, right? So one form has you have d directions. So and then the discrete measure also look like exponential of some action. I don't want to spend too much time to define this action, but basically it's some sort of nearest neighbor interaction. So basically here we want to look at a plaquette and the product of the spins along all the four edges. Okay, so we have a well-defined measure. Right? So unlike continuum Yang-Mills, here on lattice, this is completely well-defined on finite lattice, right? Because it's a finite dimension. Okay, what we do is we look at the corresponding dynamic for this lattice model, and we show that as lattice spacing go to 0, it converges to our continuum dynamic. This dynamic has the same form. Basically, it's a gradient of the action plus derivative Brownian motion. So this Brownian motion is a Brownian motion on Lie group. There's also the third trick. We never mentioned this. Okay, let's just ignore this in this talk. Okay, so this is a dynamic on the product Lie group, right? So every edge will have a Lie group valued spin. So this whole dynamic live on the product of all the Lie group over all the edges. So what's nice for this dynamic is that we know that this measure, right? We can explicitly check this measure is just invariant measure for this dynamic, and we want to pass this story to the continuum. And of course the first thing to do is to rewrite this discrete model, discrete dynamic, as a approximate SPD, right? So we want to somehow see that this dynamic is approximately the stochastic PD, maybe with a lot of error terms, and then we show that as lattice spacing go to 0, maybe remainder term go to 0 or something. Right? But actually, it turns out this to be more challenging because the discrete model actually take a value in the Lie group, right? So remember, in this continuum setting, the A take value in the Lie algebra. But on lattice, it actually take value in Lie group. Actually, this not something. This is actually something natural because actually, if we want to discretize the model to preserve the gauge symmetry, there's nothing else to do. We have to make the field taken value in the Lie group in some sense. Recall that the relation between Lie group and the Lie algebra is the following. So exponential of Lie algebra element give us a Lie group element. So here what's going on is that the epsilon here is the lattice spacing, and you should think of the scaling is such that as epsilon go to 0, the Lie algebra element, right? So the A here becomes smaller and smaller, right? So epsilon A becomes smaller and smaller, so that eventually we are around the identity element of the Lie group. So essentially, you're sort of going from the Lie algebra to the Lie algebra is the tangent space at the identity of Lie group. So essentially, by the scaling, we're going from the neighborhood of the Lie group to the tangent space around the identity, which is the Lie algebra. Um, in order to really make precise of this argument, we actually use some geometry. So the dynamic lives here, right? So we want to actually derive a dynamic which lives here. The dynamic gradient flow plus noise, and the gradient and noise, actually, they both depend on the remaining metric. And so what we do is to basically, so here this is a Lie group, of course, it's a remaining manifold. And we want to pull back this remaining metric from here to here, right? So in doing that, we actually make this Lie algebra to be an isometric remaining manifold as a Lie group. So once we have done that, we can just take the gradient flow, right? So we can just pull back this action function from here to the Lie algebra, and then we take the gradient flow plus the noise on the Lie algebra, because here the gradient and the noise they are the right gradient and the right noise with respect to the right remaining metric in some sense. Okay, so after a lot of work, we really see that on the Lie algebra, we do have a approximate SPD. Let me mention that this sort of geometric derivation, geometric finite dimensional truncation, actually appear in some other context. For example, Bjorn Breman also recent paper which studied so-called wave map equation. So the wave map taking value in the Lie group. It's a very different model, totally different setting. But actually there he also used some geometric, that also used some finite dimensional truncation such that the truncation, respects some sort of geometric covariant structure. So eventually we prove that actually so all the remainders actually they don't simply vanish. They actually contribute to the to a CA, which is exactly the same as the renormalization constant, right? It's in the same form, but it's not this is not so in some sense not a renormalization. It's in some sense a residue from those remainders. So those remainders don't simply vanish. They still contribute something. So the next step is to show that the sort of residue from these remainders, they're actually the same as the renormalization constant that we mentioned before, and therefore we can identify the limit. So the key idea here is that actually there's only one renormalization C, which gave us gauge covariant dynamic. Okay, so those discrete models, we know they're gauge equivalent, they're gauge invariant. So if we know the limit, there's only one unique limit, which is gauge invariant, then automatically those limit of the discrete models, there's the right limit. Okay, so the key here is to identify there's a unique renormalization, which is gauge invariant. And here, actually, I don't have too much time, but the key idea is to use the observable. So there's something called a gauge invariant observable. For example, in abelian case, the observable is simply the line integral. So line integral of the A. Okay, so the idea here is a well-known idea in multivariable calculus that everyone knows, which is shifting vector field by gradient doesn't change the loop integral, right? So this is the vector calculus. So here is this this object which is invariant under gauge transformation. So in order to show that there's a unique C which give us gauge invariant solution. We just need to argue that with the wrong choice of C, the solution is not gauge equivalent. Um, to show that AT and BT are not gauge equivalent, since the Wilson loop here is a gauge invariant observable, we just need to find one single loop so that the two Wilson loop, right, two gauge invariant observables actually are not equal for AT and for two solutions. So we managed to prove this. Okay. I'm not going to give any details, but I just remark that actually using the idea of using observables to prove certain properties of stochastic PDE or measures actually um, is a general idea. For example, there is a recent paper by Martin Heyer and other people. They also use some sort of observable to show whether the law of solution to a certain nonlinear stochastic PD is singular or not with respect to the linear equation. There are many applications of using observables to prove something. Okay. In the end, I mentioned that in order to implement Bourgain's argument, we also need to remember there is a Markov inequality which relies on the moment bound of the invariant measure, right? So here we have this degree of freedom. We have this gauge transformation. So the question is under which gauge we can prove such moment bound. So for Yang-Mills there, so I mentioned axial gauge. Under axial gauge in 2D, the measure become Gaussian. But this is not a good gauge because actually now you see there's only a D2, right? So only a derivative in the second direction. So in the first direction is a very singular. So it's two singulars. So we want the measure to be supported on C0 minus. Another gauge is called Coulomb gauge. Coulomb gauge says that maybe you can choose a good gauge such that the divergence A is zero. Turns out that if this is true, then we do have a like C0 minus good regularity. But in general, actually, it's not a guarantee that we can choose a Coulomb gauge. Okay. So in this paper by Ilya, actually, he found a sort of mix of two gauge fixing. In some sense, large scale we choose a axial gauge, and small scale we choose a Coulomb gauge. And then turns out that we can fix this gauge and prove a bound which says that after this gauge transformation on the lattice, we can bound a certain norm of A, certain very rough norm of A, by a gauge invariant quantity. Then in order to bound the moments, we just need to bound the moments on the right-hand side. And since right-hand side is a gauge invariant quantity, we just need to choose a good gauge to bound the moments of the and here we just need to choose an axial gauge. Because the axial gauge, it becomes Gaussian measure, so bounding moments of the right-hand side boils down to some standard and or some sort of estimate on random about random walks on Lie group. I'll just stop here. Thank you very much.
Thank you very much, Al, for this really interesting talk. Are there questions? Francesco?
Yes. Ciao. Listen, at the beginning, you showed that you were able to build the coupling between the free field and the measure, and the gauge measure, right? The
Yeah.
regular coupling, I mean, this here.
Oh, here. Yeah.
But this means the measure is not absolutely continuous with respect to the Gaussian free field, or it's due to
Right.
the technique?
It's not absolutely continuous with respect to Gaussian free field.
I see. I see. And this is due to the derivative of So because this is very different to respect to the scalar case, I mean, and this is due to the derivative, the first order derivative of the field.
Yes, yes. I think in this context, nothing is written down, strictly speaking. So, oh, okay, maybe you can see, yeah, this is not in the Karman-Martin space, right? That's
No,
why.
no, no. Only yeah, I guess it like that only
Yeah.
because of this, not for
So,
other reason.
I think, yeah, it's essentially for this derivative term. Otherwise, if we only have the non-derivative term, then it looks like a 5-4, basically. In 2D, the regularity is the same as 5-4. Yeah, because
Okay, I see.
then we only have an 8.
Uh, Second question, sorry. You mentioned the strong Markov property. I suppose that this is essential to prove uniqueness of the invariant measure, right?
Yes, yes, yes. The what Markov property?
Strong Markov, strong Feller, sorry.
Oh, strong, yeah, yeah, strong Feller. Yes, yes, yes.
But is it used in other points of the proof, or for example, the existence part, the long time existence could be, in principle, be extended to the full space case, or there are some essential in 2D, I mean.
We don't know how to extend to full space. Yeah, the strong Feller only holds. We only know on the torus. And yeah, it's a standard result. Well, it's a general result by Martin and Jonathan Martelli. So for general SCAS PD, we have such a strong Feller, but
No,
only.
no, the strong Feller I know, but I mean, because my question was, yeah, so the problem in the full space is only a problem due to the analytical part of the proof, or this more probabilistic part with the Bourgain argument also,
Uh,
or maybe both. I
both,
have no idea.
both, both. I think both. I mean, first we don't know how to even don't know yet how to prove a local solution on the full
Mhm.
space analytical part, and even we know it's not clear how to directly show strong failure on a full space, right? Usually you need some sort of correlation decay or
Yeah.
some sort of, uh, yeah, some
Maybe
sort of spatial mixing.
maybe just a comment. I think a strong Feller is really just used to get like uniqueness of the invariant measure. So like this Bourgain argument, for example, doesn't use that in any sense. And even
Okay, so in principle, if you were able to prove the exist so the short time existence on the full space, the argument should work.
uh, the Bourgain, if you had moment bounds in the invariant measure and you could prove local existence, I think
Okay,
Bourgain's argument should continue over.
okay, I see. Thank you.
Yeah.
Yeah.
Alessandra has a question. Alessandra, you there? Maybe not. I don't know. Are there other questions or comments? Alessandra, if you like, you can write the question in the chat. All right. You can try to write that in the chat.
Maybe just also another question about Francesco's. I think actually this non absolute continuity with respect to the GFF is actually really not known for dimension 2. I think you don't expect it because of this C1, but it's not actually known.
So maybe combining the argument by Eirer and I don't Kusuoka and the other person that I don't remember with your own, it's possible to prove something like that?
Um, I'm not really, yeah, I'm not really sure.
In some senses, no, I think because Thierry Levy has a paper which shows that if you change the coupling, then the measures are mutually singular. So in principle, you can choose zero coupling, then the Gaussian free field. So maybe that's in some sense.
But that's already true with the. Isn't it already true for the Gaussian free field somehow itself? Like at different couplings, it's.
Yeah, I think he didn't mention you can choose coupling to be zero and get Gaussian or something, but yeah, I think according to what his paper said, if you change the coupling, then you get a singular measure. Of course, you can change the coupling to zero, I suppose. I mean, something along that line should work.
Hmm.
But yeah, indeed, there's nothing written like clear written that's
Yeah,
singular.
it's not.
Alessandra, if you can talk, please talk. Otherwise, I can read what you
Do you
wrote.
hear me? Do you hear me now? I
Yeah,
had
Yeah.
problems
very
with
well.
my. Okay, so are your theoretical results also related to Feynman propagator scattering rates? So can you make a theoretical connection, rigorous?
Yeah. Okay. That's a good. Yeah. So in our stochastic, in our stochastic setting, um, yeah. So maybe some of us know some QFT, right? So in QFT, we do we look at the Gaussian part. We view the covariance as a Feynman propagator and do a Feynman diagram expansion. Here the linear part corresponding to the propagator. Um, so the linear part, for example, if we only solve the linear equation, right? So this part plus the noise, then the solution is just the kernel, the heat kernel for this heat equation, right? Heat kernel convolution with the Cassi. And then if you compute the two-point correlation function at tx and ty, for example, of the linear solution, then the correlation function is exactly the Green's function, the propagator in quantum field theory.
Okay, thank you. Thanks a lot.
Sorry. Are there other questions? If not, let's thank our speaker again. Thank you very much for the very interesting talk.
Thank you.
Thank you a lot for the very interesting talk and accepting the invitations.
Yeah,
I want to mention
format very nice. There's a break, so we can ask questions. I don't.
Yeah. Let me mention the next